Hey Level 2s and welcome back to 2.5 Organic Chemistry. We're up to Lesson 7 Part A. So we're covering quite a lot in this lesson today, so we can do some practical work in the coming lessons. So what are we covering? We're going to talk about those physical properties of alkenes. So we're into the alkene functional group, and it's always the same three that I cover: melting and boiling point, solubility and conductivity. Then we're going to talk about some chemical reactions of alkenes, so combustion, addition and oxidation. And there's also polymerization, but I can't fit that all into one lesson, so we'll do that in a lesson's time. So quick do now. So here are some formula of the first 6 alkenes. And it shows the melting and boiling point, and I'd really love you to pause this video and describe this trend. Okay, so now I'm going to go through this with you. Hopefully you can see that as the structure gets bigger, the melting and boiling points go up. And the reason why, remember we spoke about this before, the larger, okay, the molecule, the stronger the intermolecular forces, okay, and therefore more energy is needed to break them. Okay, so the larger the molecule, the stronger the intermolecular forces between the molecules, and the more energy is needed to break them. And that's a common trend, and you'll see it come up a lot. Okay, physical properties of alkenes. So we always talk about boiling point. Okay, so let's talk about that quickly. So boiling point is very similar to alkanes because they are non-polar molecules and they're really simple. So the two trends when we talk about boiling point is the size, and that's just what we were talking about there. So that do now was the start of that discussion. So as the size increases, the intermolecular force strength goes up, and the melting point and boiling point goes up. And the other thing is the shape. So you remember the other day that a straight chain versus a branch chain. So straight chains compact together more closely compared to branch chains, which end up being a bit more circular in shape or clunky in shape. So there's more surface area with a straight chain, which means stronger intermolecular forces, which means more energy and therefore a higher boiling point. So those are the two main things that we need to recognize with alkenes. The next is solubility in water. Now, because they're non-polar, they will not dissolve in water. And so that means that the intermolecular forces between the alkene and the alkene, and the intermolecular forces between the water and water are stronger than the intermolecular forces that can occur between the alkene and water. Okay, and that all comes back to 2.4. So I hope that makes sense. So these properties don't take long to go through each functional group because they all make sense and they're based off the structure, and we've already done structure and bonding. So the final part is if they were acidic or basic, and this is factual. They're either acidic or basic, and the answer is they're not. They're just neutral, okay? So therefore, they will not conduct electricity, okay? And the reason why is because they do not dissociate in water, which is something I'll teach you a bit later on. So they are neutral, so we don't need to worry about that one. Okay, so boiling points, so this is what we were just talking about. They've generally got low boiling points like alkanes because they're just non-polar. But as I said, as the size gets bigger, as the chain length increases, the strength of the intermolecular forces increases, and more energy is required to break those bonds. So whenever you're talking about boiling point, you must link in the energy and the strength of the intermolecular forces. So that's why ethene will have a lower boiling point than butene, because it's smaller. Okay, the second fact I spoke to you about was that straight chain alkenes compact together better because there's a greater surface area, and therefore will have a higher boiling point than branch alkenes. I hope that makes sense. So your small alkenes, because they've got low boiling points, they will be gases at room temperatures, and higher mass alkenes will be liquids at room temperature. So your ethene, propene and butene are all gases at room temperature because they're small chain molecules, and as it gets bigger, it'll take more energy to break those intermolecular forces, and they'll be liquids. Okay, so let's just discuss these boiling points here. So this one's really interesting, actually. This one's quite good. So it's saying, why does but-1-ene, and we don't name it like this, but this has just been snapped off the internet. Okay, so but-1-ene is what we would call it, but-1-ene. and butene. So which one's got the bigger boiling point here? And if you look here, butene has a higher boiling point than cis-butene. And if we just have a look at why that might be, butene, it's drawn a little bit funny here, but butene, straight chain, okay? And if you see here, butene, the cis, even though it's kind of a straight chain, you can see that these two methyl groups are stuck to one side of the structure because it's a cis isomer, and that kind of makes it a bit clunkier, like almost like a branch chain molecule. So this one, because these are just hydrogens, these are able just to sit like a straight chain, and this one is in fact more branchy, can't pack together as tightly, so there's less surface area for this one here. Now this is pushing into kind of a level 3 type question. I just thought I'd show it to you to expose you to some proper chemistry here. So because this one's cis and it's got these big groups on one side, it means it's quite clunky, and it ends up being a bit like a branch molecule compared to butene, which is more straight, and so therefore the straight can pack together more closely, greater surface area, stronger intermolecular forces, more energy to break. Okay, so physical properties continue. They're not soluble in water because they're non-polar and they'll float on top just like alkanes, and they're not acidic or basic, so they won't produce ions in water. Easy peasy. And you'll see these trends are very similar as we go through, and I repeat it every time. Okay, excellent. So now we can start talking about the 4 reactions that alkenes undergo. We're not going to be doing polymerization today, but we're going to do combustion, addition, and oxidation. So what is a combustion reaction? So remember we learnt last time that combustion means to burn in oxygen, and there are 2 types of combustion reaction. There's complete combustion when there's plenty of oxygen available, and there's incomplete combustion when there's limited oxygen available. So when there's plenty of oxygen available, we always produce, and apologies, I've done this again, I must have copied these, the water's liquid state. Not that that matters at this level because states come up at level 3, but we're best to be correct here. So if you look here, when there's plenty of oxygen, we get complete combustion occurring, and complete combustion produces CO2 and water. Incomplete produces CO and carbon. And remember, just a bit of a recap from last time, we spoke about the fact that carbon monoxide is a toxic gas because that actually binds to your hemoglobin and stops oxygen binding. So it actually means you pass out and you can actually die from carbon monoxide poisoning. And carbon itself can be like an asthma irritant, or it can actually be it is carcinogenic, so it can cause cancer. So let's go through how we balance these equations. So here's ethene, and we know we're adding oxygen, and oxygen exists as O2. You always balance your carbons first. So you've got 2 carbons in C2H4, so you're going to put a 2 here for CO2. The next thing you're going to balance is the hydrogens. You've got 4 hydrogens, so you need to do 2 H2Os here. The final step is to balance the oxygens. You've got 2 times 2 makes 4, plus 2, so that's 6, and so we need to do 3 O2s to make 6 oxygens. So I hope that makes sense. Let's go through and balance these bottom 2. So again, you need 2 carbons, so 2 CO. You've got 4 hydrogens, so you need 2 waters, and then you need to balance your oxygens. You've got 2 plus 2, so you need 2 O2, okay, to make 4 on each side. Again, 2, 2, 4, so you need 2, and then we balance the oxygens, and you've only got the 2 from water, so it's just O2. And you can see these have got less oxygen than this here. That's why it's limited oxygen. That's when they are produced. So combustion reactions, to be honest, they don't really come up at level 2, but you really need to understand them and know them. It's more of a level 1 topic because that's what's heavily covered in the level 1 achievement standard, but you still need to be able to do them for level 2. Okay, addition. So because alkenes are unsaturated, and what that means is that they don't have the maximum amount of hydrogens surrounding them, or atoms surrounding them, they've got a double bond. And so what that does is that makes them quite reactive, and this double covalent bond can actually break and single covalent bonds can be produced. And what happens is you end up making a saturated compound. And so if you look here, if we break this double bond and we can add an X and Y's just showing any atoms, they will then bond, and you end up making 1, 2, 3 single covalent bonds from something that had a double bond, which is quite cool. And you can see the X atom and the Y atom add on, and that's why it's called an addition reaction. So there are 4 types of addition reaction. So there's hydrogenation, and just like that word kind of sounds, hydrogen, it's adding H2. So if you add H2 to an alkene, you're going to produce an alkane, and we're going to go through that. Halogenation, so that's if you add a halogen, so Cl2 or Br2 are the ones that we commonly add, and if you add Cl2 or Br2 to an alkene, you're going to form a haloalkane, and it's actually going to be a dihaloalkane because both atoms will go on. You can add a hydrogen halide, which means hydrogen with a halogen, so HCl or HBr, and you'll produce just a haloalkane again. Won't be a di one because there's just a single atom. And hydration, hopefully you can think about water. And so if we add water to an alkene, you'll end up making an alcohol. So there's so many reactions alkenes undergo, which makes them really cool. And these are the types we're going to do now. So first, hydrogenation. So this is when 2 hydrogen atoms are added across the double bond of an alkene. Okay, and so what you can see here is this double bond breaks, a single C-C bond forms, and the 2 hydrogens pop on, and it goes from ethene to ethane. So quite a simple reaction. You do need to note that this has a catalyst. Now, for those who haven't heard of this term before, a catalyst is something that speeds up the rate of the reaction. Okay, and we're not going to go through now how it all works, but we add catalysts to speed up the rate of the reaction, and they don't get used up in the reaction, so they'll just stay as is. And so the catalyst is either nickel or, nickel and 150 degrees, so you have to do both, or it's just platinum, okay? And you have to know those, you have to know the catalysts, but don't forget, we're just learning a lot today and we'll recap the whole topic. So you do need a catalyst for this one. It's either nickel and 150 degrees or platinum. So the next is halogenation. So this is the addition of 2 halogen atoms across the double bond. It's normally chlorine or bromine, okay? So if we have ethene here and we add bromine, both bromine atoms jump on, so we end up forming a dihaloalkane, and so we know how to name this, which is 1,2-dibromoethane. How cool is that? So unsaturated, because there's atoms that can still be added, and saturated, because there's no more atoms that can be added to this. And so here's just another example showing you the 2. So this one here is ethene, and if we add Cl2, both chlorines go on, and this is propene. And so just remember that the double bond breaks and the atoms join on to where that double bond was. I hope that makes sense. So what's quite cool is we can actually test for saturation between an alkene and alkane using a specific test, and this comes up quite a lot in your exams, and it's called the bromine test. And so you may not be aware, but I'm going to show you some bromine in the lab, and bromine water is an orangey brown color. It looks like this. So bromine water is an orangey brown color, so when it's just the aqueous solution of it. And what happens is we've just previously seen from learning alkanes and alkenes that both of those alkanes and alkenes will react with bromine water. But you'll remember when I taught you the substitution reaction for alkanes, alkanes will only react with bromine water if UV light is present. It has to have UV light present, and it's a slow reaction. Whereas though alkenes will react super quickly and they don't need UV light. So we can actually use this bromine test and the speed of the reaction to determine whether we have an alkane or an alkene present. So if we add bromine water to both an alkane and alkene, they'll both go orange straight away because that's from the bromine water. And if we leave them a few minutes, the alkene will decolorize to a colorless solution and the alkane won't because it's a slow reaction and it needs to have UV light. So I hope that makes sense. That's called a bromine test, and that's how we can distinguish between an alkane and an alkene. Alkene, nice and quick, no UV light. Alkane, slow and needs UV light. Okay team, I'll be back soon for part B of this video and the rest of the reactions. Okay, bye.